So I feel like I'm working. There's a bit to get through. If I do start talking too quickly around then just wait and slow down. But now we're going to have a look at some of the specialist kind of equipment we've got available in other places in terms of the systems and the gas environments and the different temperatures. Not ambient pressure, that's going to be covered later, just gases in UHD-based systems. So obviously you can imagine that it's quite a bit of a problem to introduce gas into SPS. We tend to work very low pressures. Any kind of gas that you introduce into the chamber is going to reduce your signal as you're increasing the number of atoms that the electrons are going to travel through. There's decreased chance of scattering, and so you're going to be losing some of your signal due to that. And so to get around this, you've kind of got two ways to touch. So you can either work at very low pressures, which are compatible with UHD systems, or as Phil mentioned in the last talk, you can move your sample between an analysis chamber and a segregated chamber for gas treatments. So first, we're going to have a quick look at some low pressure labour studies on a UHD system. So this typically involves a kind of dedicated gas manifold in which you can charge with gas or vapour if you freeze thaw and use sublime vapours, and then a leak valve that allows you to manually kind of control low pressure dosing into an analysis chamber. For those of you that aren't scientists or aren't familiar with terminology, one of the common units in these kind of experiments is a langware, and this is kind of semi-quantitative really. It's one langware is equal to 10 to the minus 4 per 1 second. But if you've done the experiment, you know it's quite difficult to accurately control what the pressure is. So they are a good guide, not necessarily perfectly quantitative.
Can you speak up?
Yeah. Just moving. Yeah, Stephen obviously mentioned it. That gets worse, but hopefully I'll hold my shirt like this. Right. So the first example I've got is some work from years ago, looking at some survey-based catalysts for transistor sterification. NGOs are very commonly used for trying to get some transistor sterification into biodiesel fuels. And with any kind of catalyst, it's just understanding the surface absorption processes is key to understanding your catalyst process and improving your catalyst and improving the way that they interact with your feedstocks. The common mechanism for this was thought to be alcohol dissociation and then subsequent removal of subsequent transistor sterification, followed by a regeneration of the catalyst with one of the ethoxy groups in this case, we have on the protonated surface. There was a little bit of debate about whether some of the processes involved were Lewis catalyzed and so some surface absorption studies were undertaken into looking at what exactly was going on. These catalysts, NGO, very good, but they generally tend to be quite low surface areas. So one of the ways around this was to look at nanoparticulate NGO, so very small, so still not super high surface areas, but certainly improved performance. The problem with the kind of nano NGOs you see down there, about 2 to 3 nanometer size, is that there wasn't too many defects on the surface. So the rock salt structure generally prefers 100 exposed facets, which are quite weakly basic and don't interact very strongly with the reactants. When you calcine those at higher temperatures, you start to improve the reactivity, you introduce more defects and expose more of the more active 111 and 110. So there were 3 molecules that were studied in terms of absorbing and seeing how they kind of interacted. And the first one was water. This is kind of a common is commonly found in a lot of biomass feedstocks to prevent lengthy separation procedures. You might just leave water in there. And looking at the dissociation on the nano NGO calcite at 700 degrees, you see a big increase in the amount of water on there. Also look at the fresh NGO just to have a look at the absorption on the nutrient-based gas, and weren't able to see any kind of absorption on there. But there was a clear increase in the oxygen for the more active catalysts. And furthermore, deconvoluting the oxygen states, you can see that there's an increase in the associated alcohol, the dissociated hydroxides on the surface, and a decrease in the strongly basic Lewis sites. So this suggests that water dissociation takes place quite prevalently on these catalysts. Now, the alcohol for the kind of model reaction here, which is tributylene and methanol. So we're using methanol alcohol as a solvent and as a reagent. So next, looking at the dissociation of methanol over these catalysts. Again, it's non-captain catalyst. But as we increase the exposure to methanol, we see more and more dissociation of the methoxy species. And again, looking at the oxygen, we see a decrease in the number of strongly basic Lewis sites. This led to a postulation that this reaction might actually be driven by in situ generated Lewis sites rather than the Lewis sites themselves. And finally, there hadn't been too many studies in terms of looking at the actual ester absorption onto the surface. So previously, some of the molecules such as water and methanol have been looked at over single crystals, not necessarily real catalysts like these, but the ester hadn't really been looked at at all. So in terms of looking at a product reaction on this, increasing the exposure again was an increase in the carbon and the oxygen, and then deconvoluting that, we actually saw quite an increase in the amount of CHX on the surface. And so DFT studies in conjunction with these suggested that the ester absorbing through this carbonyl function onto the surface could then promote some CH proton cleavage, and that led to a postulation that this would actually deactivate catalyst. So when we get esters dissociatively absorbing on the strong basic sites, this could lead to on-stream deactivation. And when we actually looked at some catalysts, we did see a massive increase in the amount of CHX. And this led to suggest that catalysts which have lots of very strongly Lewis acidic sites could actually set poison and deactivate on on-stream. Okay, so on to higher pressure analysis. So that was a quick tour of some of the gas stations. This is an example of one of the high pressure cells. So this is the catalysis cell on a process instrument, which Dave's got recorded. And we've used for a couple of experiments. We're just going to have a quick go through here. So this is an example of work from a few years ago looking at gold on titanium and the generation of strong amount supporting interactions. So these are quite well known. I'm sure everyone here is aware of SMSIs, very well known for PGMs, and they promote things like charge transfer and increase activity and prevent deactivation of catalysts. Historically, crude body metals have not been known to produce SMSI effects so much. There were a couple of examples where they've been inferred in the literature for some silver on titanium, but certainly for gold on titanium, they haven't been observed in the past. So some collaborators had some gold on titanium catalysts, and they reduced them under hydrogen. They saw much increased stability and activity for CO oxidation, and so we kind of wanted to understand what was going on. And so a combination of TRIPS and XPS was performed to understand this. When we did the XPS of the reduced system, so these were reduced at 500 degrees C in the hydrogen, and we can actually see a shift in the gold. So we see some delta positive gold sites indicative of charge transfer between the TiO2 overlayers, and also we see a concomitant decrease in the signal from the gold tubing because we've got these titanium overlays, which are then attenuated in gold seams. And this was about 33%, which was calculated to be about 0.7 nanometers thickness, which is roughly 2 monolayers of titanium. But very importantly, as you know, with SMSI effects, these should be reversible. When we then treated them with oxygen, we found that we could weaken our signal, and we also sort of shift back towards slightly negative binding energy. So the second example I've got is for some forming of nickel. So nickel catalysts, I know some people deal on DRM and nickel catalysts, you're probably well aware of. They tend to cope and deactivate, which is generally over equal metal sites. And again, some collaborators have developed a new support for these, which has the ability to stabilize some small cluster and single site nickel atoms, which were quite resistant to coking, certainly much more than on other supports. And in order to kind of probe what was going on, we took this down to Cardiff to work with Dave, and we had some high and low loadings of nickel on a hydroxyapatite support, and then this hydroxyapatite cerium mixture. With the high loading catalyst, because we've got big particles of nickel, these tend to reduce readily. So for both supports, they reduce down to the metal very quickly. When we looked at the low loadings, so the small clusters and the single site catalysts, these were very resistant to reduction for both samples really, but much more for this hydroxyapatite cerium composite. Even for the hydroxyapatite alone, we still see some reduction and version of this formation of nickel metal, which is going to produce coke. But for the hydroxyapatite cerium composite, you can see it's very much keeping its oxidation state in check. Okay, so obviously gas dosing is a little bit more complicated. We just want to heat. This is much simpler. Most modern industries, or a lot of modern industries, have some kind of capability. This is actually our heating stage in our critical plant. So the example I've got for simple heating was some collaborators from the US that had some tin and copper doped nickel loaded aluminas, which they were using for liquid diesel conversion. And the 5% copper was found to be particularly effective. And they had some TPR results which suggested that there was some improved reducibility. But we wanted to have a look at XPS and see how the oxidation states tracked with the TPRs. And so we basically put in the XPS and heated them following this TPR reduction, and we can see the different equal states in each temperature range in the TPR, which allows us to kind of use the resulting combination to understand something in the catalyst. So straight away we could see from the decomposition that the copper doped materials were much more reducible. We had much more surface nickel metal, and when we heated them up, this was also quite resistant to oxidation and to losing those surface metals compared to the pure nickel, which generally has not too much nickel metal in there, and it didn't really change the product. But it's just a nice example of how heating in XPS can be used with TPR to really help understand what changes are going on in your catalyst and what kind of exercise are there. So finally, I'm just going to quickly mention power XPS. So we've talked a bit about heating, we've done this as well. This is a little bit more experimentally challenging. I know there's a couple of people in here that have done some power XPS that can attest to it. It is a bit of pain sometimes, but we are working on ways to improve this. And it does enable you to analyze things like volatile materials. And for example, if you've got post-reaction with catalysts and you want to look at resorts on the surface, or even reaction solutions, liquid precursors, that kind of thing, provided the volatility is compatible with the experimental setup. And the main progress is going to enable you to study those in detail. So as I say, it's quite experimentally difficult. So this is something that we've recently been designing and implementing at Harwell to try and improve our experimental capabilities and get more reliable power XPS. So I will quickly run through an example of where this is have been pollution. Reference sections are quite important, particularly when we've got quite psychological challenging materials, so getting a good reference section and able to get really accurate or much more accurate quantitative analysis. Modification of High-Sense area surface, you've got something that can be interesting, allows you to kind of combine a High-Sense area with a good support. And outside the one way to do this by wet chemical methods. But in order to understand what kind of layers we're building up, reference should be pretty important. So we fixed in titanium oxides typically down to about -110, which was just about enough to stabilize it in UHP and get some nice. And we did end up with very nice symmetric, beautiful looking spectrum. But what was also and when we looked at the valence band, we could see what we're currently trying to calculate exactly what the number we believe through electrical as well. One thing to be careful of if you are managing products is you just need to be thinking about experiments, parameters, what kind of time you're going to need. As in liquids, you see that things can tend to reduce slightly more readily than in our Harwell. So if you say, come speak to us, we obviously do more and more of this, but they might not be quick experiments. It's basically quite helpful to show things. So I will finish with 10. So if there's any questions.
There's one question online so far, which is, are the satellite peaks necessary for all the elements to fit the pattern, and where do they come from?
So not every element is satellite peaks, but things like first-order transition methods generally tend to be quite satellite heavy. You don't have to have a detailed understanding of the multiplets and the satellites there. If you've got a good reference spectrum, what you can kind of do is linear combination fit. So just get the spectral shapes and get either semi-quantitative or qualitative analysis out, depending on what kind of what you're interested in and what you actually need. But the vast majority of samples that you look at, you won't need to really worry about things like second row, third row transition methods are not the issue.
Hope that answers your question, anonymous attendee.
Mark, thanks, Mark. I see that you could distinguish between methanol, carbon, and methoxycarbon.
Yes.
What is the stability of methoxy species under X-ray? Are they stable or do they dissolve?
So those things a long time ago. So they were actually done on a non-monoclinic X-ray source, so that the actual intensity of non-monoclinic X-rays was considerably higher, which means you can kind of use lower fluxes. I don't know how stable they will be in the sources at a high power, to be honest.
Okay.
But they were stable than non-monoclinic X-rays.
Okay, thanks. Because I'm very much interested in the topic, and that's the reason. Thank you very much.
Yeah, so that's a really good question. And we don't know the answer because it depends on the system.
Okay.
But it's really good to raise that because that's the sort of thing you've got to watch out for.
Yeah. Okay, thanks.
So someone is asking, would the peaks of material shift position with the low temperature cryo XPS?
It's a very good question, and it's something that is so we've actually been doing a little bit of work on. You do see changes in the properties in terms of broadly and as long as you put something to calibrate to, it shouldn't be an issue.
With your cryo, can you just say a bit more about how the transfer, are you dosing onto something that's cold, or are you manipulating it in under cryo conditions, and how stable is that manipulation?
Yeah, so the current system is we cool in air, and we're kind of limited to about -30 because of transfer between the stage and the air. The new system that we've just designed with, let's track it back, should enable us to pull much more, get them to much lower temperatures in air before we start pumping. Because the problem we've been having is we get down to -30 and then we need to start pumping, and then the more volatile stuff comes on. Yeah, so but the new system is gonna get around that and will sit on a stud, which is pre-cooled and then transferred on the same stud and cooling continued all the way to the X-ray analysis. So there's no more questions.